everybody. Well, I will try to keep you all awake. I want to talk a little bit about how the lines are starting to blur between what constitutes the real world and what constitutes the virtual world. And this isn't really so much about how you would implement some of these things, but some of the things that we have to consider. But I want to start with a history lesson, because people talk about the Internet of Things and all of this, all of these devices and sensors as if they're something new, but they really aren't new. For those who have worked in industrial automation and transportation automation, we've been doing this for a long time. Cars, subways, factories, autonomous vehicles, not autonomous in the same way. One of my first jobs, there was actually the mail cart that followed a little chemical trail, and it had sensors so it knew not to run into people, and that was an autonomous vehicle. And we had this back longer than I care to admit, being my first job. We've had embedded systems, we've had programmable controllers, we've had robots for a long time, and actuators, and all of these things that we're talking about. And I want to tell you a story about my first real job. I worked in warehouse automation, and we were going around retrofitting warehouses. And the first of these warehouse systems that I worked on was actually we were retrofitting the original, one of the first automated warehouses that had been installed anywhere in the world. It was run on an IBM 1800. I actually saw core memory. Yeah. It was interesting because we replaced this massive thing with two PDP-1124s. And we were so excited when they said, instead of having 8K of memory, you can have 16. And that was a big day for us. The second warehouse I worked on, though, was modern warehouse technology. They were building a new factory, building a new warehouse. And yet, many of the principles were still the same. It was a whole lot easier to program because we had more of the smarts in the actual warehouse equipment instead of having to put it into an Allen Bradley programmable controller. But still, fundamentally, it was the same kind of thing. It was the computer system that was deciding what was happening, and there were a few sensors and a few very basic actuators that would allow us to know where things were in the warehouse. The old system had a very dumb algorithm for determining if a bin was full. It would try to put something in and push and push and push. And if the motor tripped, the bin is full, which doesn't work very well if you've got something very heavy on the pallet and something very light in the bin. The radical innovation in this new warehouse was the fact that they had a sensor, and they could see if the sensor was blocked. So this isn't new. But there are some things that are new, and I want to talk through one concrete example to show you sort of the progression that we're going through in one particular industry. So let's think about healthcare. We start with a doctor has a physical office, and she sees patients in that physical office, and she touches and talks and diagnoses and draws blood and gives injections and all of those things in that physical office. And that's where we started. And there were some things that started to be done differently. One example of this, there was a company that was based in India that they started doing radiology, the scans of the x-rays with radiologists that were based in India. And that was wonderful because the middle of the night in the US is actually a good working hour in India. And so they started doing that examination, and that particular thing actually didn't require you to be able to see and touch the patient. They just sent the images. But this was now taking it outside the realm of the hospital and to a completely different continent. You can think about telepresence and how you could now start to separate at least the conversations between the doctor and the patient. But that's not terribly useful because the doctor still has to poke and prod. You're not going to be able to talk to someone and know whether they have appendicitis or not. And then you might have something like artificial reality with the doctor talking to a village health worker who is actually sitting there with the patient. Maybe virtual reality with a doctor, a patient, and a robot. Or maybe eventually you dispense with the doctor for some things that are routine enough. So this is a progression of how we're bringing people further and further away from some of these exchanges. So the lines are blurring between what is the physical world and what is the digital world. And this is a quote from one of the early IoT pioneers. He talks about this as computation and data communication embedded in and distributed through our entire environment. So this is not just data, this is also computation, and it's spread everywhere with people, with sensors, with actuators, embedded in and distributed through our entire environment. So how have things changed? Why is this world now so different than it was when I first started? The models that we had of the real world of the warehouse were incredibly primitive. We had very simple diagrams or models within the system that knew where the different loads were in the warehouse and knew the status of different things. The models that we can build now of the physical world are of much higher fidelity. So we know much more precisely where things are. And we can measure things, and we can store so much more than we could before. We've got greater flexibility, in part because of the precision of some of these actuators, to affect the real world from the digital world. So we can make decisions like we did before, but we have a much greater ability to do fine-grained manipulation in the physical world as opposed to the pretty coarse-grained we could do before. We have much better ways for humans to interact with computers than we did before, and people are much more comfortable interacting with computers than they were. We have much better feedback loops. The quality of the sensor data that we can get back in is much better. And most importantly, I think, we have much more autonomy in the things on the edge and their ability to collaborate with each other. In those older systems, it was pretty much a hub and spoke. You had the controller and it went and talked to the edge. Now, things in the edge can actually collaborate with each other. They can act much more autonomously, and you can actually distribute control in a way that it just wasn't feasible before. So what has enabled all of this? Moore's Law. Specifically, the processing power that we have available to us with the power efficiency. It means we can deliver much more compute power to the edge than we ever could before. You can do so much more simply because we've got increased processor capacity, and these things can be distributed physically much more widely because of the better power. And this is all at significantly reduced cost. There was a reason that they were trying to keep us in to 8K just because of the cost of increasing memory. We wouldn't even think about the cost of 8K of memory now. Ubiquitous and improved communication infrastructure. These devices, it's much easier for them to communicate to each other and back to the mothership than it ever was before. Some would assert cloud computing. There's an argument for that. Certainly the ability to collect and manipulate data at scale is critical. You could make an argument that you could have done that regardless, but I think the availability, particularly of these geographically dispersed compute clouds, makes it easier to start conceiving of these systems that have much broader geographic spread. Smartphones and their impact, in part, on the way people perceive technology. Technology has invaded the human existence in a way that, for many people, it just wasn't conceivable that this would actually happen in that way, that people would start to think about implants, having devices implanted into themselves. We've changed our relationship with technology, and that started really with the smartphone. And of course, distributed computing techniques. And for those of you who have been around long enough, there's nothing new here. People who learned about systems many, many years ago had to worry about how do you get two systems to collaborate with each other? How do you worry about things like what time is it? Did something happen before something else? What about unreliable communication? These are not new problems, but the fact that we know how to do this is part of what enables this. But we're now having to do it on a much, much larger scale than we ever thought about before. So what kinds of things might we see? There's a progression here, and we're seeing this impact almost every part of our life. We started a couple of years ago talking about quantified self, and that has very quickly moved to smart self. We have smart homes, smart businesses and factories, smart infrastructure, smart cities, and effectively a smart ecosystem. So let's talk about each of these and what is happening there. And you're going to see some common threads throughout these different applications. Smart self, health monitors, activity monitors. I suspect that there are very few people in this room that do not have some kind of step counting technology at work at the moment. Ironically, this one, when I give talks, it detects the activity of swimming. I guess that means I move my hands around a lot. Entertainment. People are bringing things along with them. But also more practical organizational support. And I'm using this in a very broad sense. I'm one of those unfortunate people. I'm terrible with names. I find it very difficult to remember whether I've met somebody or not, let alone what their name might be. So I keep thinking, isn't it going to be wonderful when the technology is such that when I come up and meet somebody, something will say to me, his name is this, and you met him here, and this is what we know about him. It's kind of scary that somebody might have all that information about some random person I'm running into at a conference, but it would at least help me, because I have a terrible time remembering people's names. But there are also more practical things. Well, gee, we detect that you have a restaurant appointment at this location, and we know you were at this location, and an accident just happened on the freeway, so if you want to make your dinner engagement, you better leave now, because traffic is bad. All of these little procedural things that people used to do, concierges, all of these are now part of how we see ourselves. Chores. All of the things that you need to do, remember your milk. Now, that also comes into smart home. Oops. Come on. And adaptive and predictive actions. So these systems are going to start to learn about us and figure out where we are creatures of habit. They're going to have a fun time with me. I'm definitely a creature of habit. I always have the same thing for lunch when I'm in the same place. And so it will start to predict, well, she's in London, therefore she is going to have an egg and cress sandwich. And so I'm going to give the list of all the stores that currently have that in stock. So what about a smart home? We're bringing this technology into our homes as well. Power consumption, monitoring. One of the people I work with, he has a monitor that tells him the power that is being used by different of his appliances so that he can figure out how he might want to manage the power consumption of his house when he goes away. Security. This is not just old-fashioned monitoring systems anymore. You've got people who have cameras that are looking inside their house. Doorbells that will show you a picture of who's ringing your doorbell. Why anybody with our current state of internet security would actually allow the internet to unlock their door, that I don't understand yet, but some people do it. Remote monitoring. You don't have to be there anymore to know what's going on. Ambiance. Dim the light bulbs, bring up the music. You can set the feel, the ambiance of your house by just talking to your house, and it will do it for you. Or maybe, because it's predicting things in the future, it's going to know that when you come home after you've had this long day of meetings, that it wants the lights to be a little low and it wants some nice calming music for you, because that's what you always do when your schedule looks like that. And again, chores. Intelligent refrigerator that can tell your milk is about to go bad. I still haven't figured out, though, why would you internet connect a toaster? I don't know what you would do with a connected toaster. Coffee machines, refrigerators, I get. The toaster, I never understood. Anybody who wants to tell me why, please come up afterwards. So smart factories and businesses. This is where we've actually had a lot more of these systems for a lot longer. Supply chain replenishment. Actually knowing what you have in stock, knowing what your ordering times are, et cetera, and doing replenishment. Again, security and remote monitoring. What is really going on in that factory? I saw another article today that they're looking at putting together a warehouse that will have 4 humans. And the humans are only there to take care of the robots. Back when I started in this business, they called them dark factories because you only turn the lights on when somebody was going to come in to maintain the equipment. We're still aspiring to that, but we're certainly getting closer and closer. And the ability, the chores and the tasks that we can now do in that context are significantly different. Power consumption. Particularly when you think about manufacturing and other processing plants, their need for power and their ability to manage the power that they draw is an enormous source of potential cost savings. These plants negotiate with the power companies on how they're going to use power, and the better they can get at understanding what their power consumption is going to be, the better off they are. Production line scheduling, we've been doing this for a long time, of course. Predictive maintenance, this is a really big one. When you can start to understand enough about how some device is acting, you can take it off the line before it actually breaks. Now, that's a real value when you think about a manufacturing plant. It's even more value when you think about it as an aircraft engine. If you can monitor enough and understand enough about how that engine works, you can say, that engine is about to fail. Don't let that plane take off. Let's fix the engine when it's on the ground, when it's a whole lot easier to fix. So predictive maintenance is a big part of this, to being able to manage for cost efficiency and for flow efficiency, but also for safety. And fully autonomous experiments, where you can actually start to conceive of, are there ways that we could reconfigure how things are working on an assembly line, for example, that might increase the efficiency? People might not have to do that. You can have an optimization algorithm that is looking at the flow in your factory. And if you've got proper control systems in there, it could reconfigure itself to be more efficient. Reconfigurable factories. Smart infrastructure. We've talked about smart grids for a long time. We still, in many ways, have a very dumb grid, but this is an obvious place to start. But other utilities as well. Water on this planet is becoming an increasingly rare commodity. I was just reading that there are about 200,000 people a year right now who are dying in India because of lack of water. That's how bad the water crisis has gotten. Again, security. When you think about all of the cameras that are out there and all of the systems that could be monitoring what's happening, we've heard a lot about how the Chinese government is actually using some of these monitoring systems, these cameras that are on sidewalks and such, to keep track of people, as well as what you might use in, say, an airport. Again, remote monitoring. What is happening in these different places? An application that has been around for a long time is thinking about having flow sensors along a pipeline so that you can detect when there might be a break in the pipeline, because obviously you're going to have a change in the rate of flow if there's a leak somewhere. A, great that we know about it. B, are there other things that we can do to maybe alter the behavior of the system to not dump nearly as much oil while we fix the leak? Traffic monitoring. Obvious. We have this already. Google Maps and the other map technology is actually pretty smart. Every time I'm in a car and you see that big red line going down the middle of the path, it's like, okay, it's going to take a while for me to get home today. Again, adaptive and predictive actions. One of the things that you get when you have this higher fidelity model and you have this ability to process all of this different data is you can start to say, okay, this is how I want to start to modify my behavior because of the environment that I'm in, and we can start to predict things that we might want to do in advance as a result of all of that information that we have. But that all relies on having that high fidelity model of the real world. Smart cities. We talk again about traffic control. Taken in conjunction with truly autonomous vehicles, we might actually solve some of our major traffic problems by routing people different ways, by telling the cars, don't all of you go to the interstate at the same time, but let's spread it across the system. Service delivery. Understanding how to do deliveries within a city is another thing that people are often talking about with smart city technology. Again, power consumption. It's a big deal. How are we distributing power across the city? Other parts of urban infrastructure like water, sewer, etc. Again, predictive maintenance. Understanding perhaps when you might want to close down a bridge so you can fix it, as opposed to it collapsing. Particularly, it's a particular problem in the US at the moment, since we've done such a dismal job of maintaining our bridges. It's not that unusual anymore to hear about bridges collapsing in North America. And adaptive services. What are the services that the citizens want to receive from the city, and how might we get that? Again, what this is looking at is the behavior of the infrastructure of the system, the control of the infrastructure of the city, but also the behavior of the humans, and how are the humans interacting in the city. And when we start to talk about the smart ecosystem, we're looking at these things as a collective. What are the ways when a human transitions from their smart home into that smart traffic grid to go to work in a smart factory and to go shop in a smart store and return home to their smart home? Although we've had attempts for different manufacturers to build very closed systems, to truly do something on the scale that we're talking about is going to require an ecosystem. Different providers of different kinds of devices and different kinds of actuators that are going to operate and allow us to live in this new blurred physical digital world, where what we perceive in the world is not just what we see, but is augmented by this virtual representation, if you will. So how are we going to do it? How are we going to do all these things? Open standards and protocol are going to be an important enabler, because, as I said, you can't have just one manufacturer who's going to be able to go from what you're wearing on your body to what's controlling the entire traffic system of a major city and everything in between. We are going to want to enable innovation in the creation of all of these devices, and they will only be able to work together if these things have open standards and protocols. That doesn't mean it's going to be easy to interface these things, but we're going to need open standards and protocols to enable this entire ecosystem to operate. And of course, distributed computing techniques. We are in an era where you can no longer make assumptions about things like, of course, the network will be up. Because even though one of the enablers is this ubiquitous and reliable communication infrastructure, in the real world, things always go wrong. And so we need to think about, it's not just distributed computing techniques, but how we think about resilience and robustness. When you're talking about the sheer scale of the number of devices that will be out there, the probability that all of them are up is vanishingly small, effectively zero. I'm too much of a mathematician to say zero because it is, in fact, possible. Just like the difference between it's impossible to win the lottery only if you never buy a ticket. It's just vanishingly small in all the other cases. It's the same kind of thing here. You have to assume that things are going to be down, that things are going to break. And so you have to design and architect your systems in such a way that they can respond to that, particularly in safety-critical applications. And if you think about that list of what I went through, more and more we are going to be putting these systems in play in places where safety is a major concern. A lot of people are talking about the decision-making around autonomous vehicles. An interesting dilemma for the manufacturers of those vehicles. People say they want the manufacturers to make vehicles that will prioritize the life of the pedestrian over the life of the driver. That's what they want the vehicle manufacturers to do. When asked what they will buy, they say they will buy cars that prioritize the life of the passenger over the life of the pedestrian. We still have a lot of these questions that have to be resolved because things will go wrong. There is nothing in all of this technology that says we fix the fundamental problem that in the real world, things are going to go wrong. And the scale of what we're talking about in terms of computer systems and hardware devices, things will be down. We're actually not used in many of our applications of thinking about that. There are still a lot of people who don't know how to write resilient and robust systems. And that's why I keep harping on these distributed computing techniques. Because we do have a generation of software engineers out there that really haven't thought about these problems. Continued improvements in data engineering. Think about the volume of data. The more we spread these sensors around, the more we try to build these higher fidelity models of the physical world, we need to have good data engineering to be able to deal with noisy data and messy data. And what do we store and what do we throw away? What is noise? It's an interesting problem when you start thinking about how sensor data comes in. How do you model what constitutes noise? In some of those feeds, it doesn't matter if you drop one. If you think about a temperature sensor that's sending in a temperature every 15 seconds, if you miss one, that's not a big deal. In some other kind of time series data, missing one is a real problem because you're going to miss a pattern. So we need to continue to think about good data engineering practices and good tools for data engineering. And I'm distinguishing this from continued improvements in artificial intelligence and machine learning. And I'm distinguishing between those two as well. When we think about the kind of machine learning models we're currently dealing with, they are learning from historical data. And I read something today, and this is the first time I'd seen it put quite this bluntly. It's what I've always felt, but I was glad to finally see in a publication that they were this blunt, that people are deploying machine learning systems that they don't understand. Now, we've known for a long time that these models are trained up in such a way very often that you can't really figure out what have they learned. My favorite example is they had this wonderful detector for wolves. It was very, very good at finding wolves until they showed a wolf in the springtime. And they realized that actually what they had was a wonderful detector for snow. But they didn't know all of the pictures that they had showed the wolves, it was wintertime. And so they had this wonderful wolf detector, then what it was really detecting was snow. And they didn't know that. So we are building these models, and we don't necessarily understand how they work. But we are relying on continued improvements to do things like this adaptive and adaptation and prediction. Increased collaboration between hardware designers, software designers, interaction designers, usability researchers, and measurement. One of the interesting things, and we have this debate within our organization a lot, how easy is it for someone who is just trained in software to solve a problem that involves hardware? And we have two camps. And the one camp says, well, you're just speaking a different language, you're just coding to a different protocol, so it's no big deal. And then there's the other camp, and I think I'm actually more in this other camp over here, which says a software engineer is going to solve a problem and approach a problem with software. Someone who also has hardware in that background is much more likely to propose a solution to a problem that has some additional hardware component. We had a discussion. There was a person we work with in India who was talking about how you might provide an early warning system for fishermen for tsunamis coming in to remote villages. And there was all of these proposals from our software people about monitoring the weather conditions and satellite and image processing and all of that. And one of our people whose background was more in electrical and mechanical engineering said, well, why don't you put a buoy out there that goes up and down when the waves start getting worse, and you can at least have an early warning that the waves are starting. None of our software people thought of anything like that because they were thinking of the problem as a software problem. The problems that we will be solving in this new world are combined hardware-software problems. And we need to think about them in that context and think about how might well-placed sensors provide us information that will help us solve this problem better. And we need to tackle things like usability in a context where we're not interacting with the computer systems in the same way anymore. That maybe, in fact, we're expecting the computer system to infer our intentions based on something that it is sensing we are doing in the real world. And the perennial problem of measurement. The models that we are going to build of the physical world are only as good as the measurements and our ability to understand the measurements that we're taking. The design of visualizations and artificial worlds. When I think about the potential for the creation of virtual worlds and worlds that people might live in for so much longer, there's a part of me that really worries. I was part of an exercise where it was one of those postcards from the future, or actually it was headlines from the future. And I guess I was feeling particularly pessimistic about the future, because the thing that first sprang to mind is 1 millionth person commits suicide in virtual world. That you can actually conceive of people creating worlds that would drive people to suicide. Now, hopefully that's not what happens. But we have a lot to learn about what are the impacts on humans with the time they spend in virtual worlds. And if what we've learned from people in video games is anything to go by, we need to figure out how to get better at designing worlds so that people don't really want to spend too much time away from the real world. And what about different ways of interacting? We've significantly expanded our ability to communicate with computer systems. But I strongly suspect that we still have a long way to go in what are the different ways that the physical world is going to be interacting with the virtual world. Because it's not just humans anymore. It's going to be other objects in the physical world that are going to be impacting that virtual world. And we have to have a society-level discussion of ethics and purpose. Why are we doing some of these things? What are we willing to accept? Do we want to allow the ethics module on the car to be parameterized? How are we going to start to deal with some of these problems? This is not something that we as technologists can decide alone, but it is our responsibility to make sure that the conversation is had. And more complex systems thinking. That's obvious. It's just we've got more and more things that are going to be interacting in more and more ways, and everything we know about chaos theory says there are going to be some weird things happening that we don't expect. So now, what are the risks? The robots are going to take over the world. You know, Terminator. There's certainly going to be an increased centralization of data and control. You can't really conceive of a purely distributed system that is going to control traffic. At least we might eventually get there, but for the moment, I think we're going to have an increase in the level of centralization of control, and that very often implies centralization of data. Humans can't keep it straight, or can't keep up at all. This is a variant of the robots take over the world, but we're already seeing that in these AI models that are being trained that people don't understand, and they're just deploying. When is that going to get us into trouble? Machine speed feedback loops. We already have seen this in trading with that wonderful company that didn't quite get all of their systems upgraded and bankrupted themselves at machine speed. In addition, we've got different failure modes that we have to take into account. Just like we talk about with microservices, there are failures in a microservices architecture that a monolith can never have. The more we increase the distribution of compute power across these networks, the more we introduce failure modes that couldn't have happened before, and we need to take care of them. Data privacy, obvious. One of the scary things about many of the early smart city initiatives is the extent to which some of the device manufacturers were willing to give all of the equipment away to the city in exchange for ownership of the citizens' data. That's a scary thought. Hopefully we can move away from that, but data privacy is a significant concern. Data ownership, similarly. Increased inequality. What is this going to do to the economic balance? And increased exposure to hardware failures. The more we rely on hardware, the more we have to think about how do we make those systems robust and resilient to failure, because they will fail. Security. The more we expose, the more we make ourselves vulnerable to people who would want to hack into things. So then why in the world would we do it? Increase productivity, efficiency, and revenue. From an economic perspective, these things make sense. Decreased cost, decreased waste, and improved environmental outcomes. One of the applications that I've read about is they're experimenting in agriculture with sensors that can determine not only how much water should be used to achieve the right level of moisture in the soil, but also what the soil actually needs in different places with respect to fertilizer. So if we can decrease the amount of chemicals that are put on our crops and decrease the utilization of water to just what's necessary, that is a significant improvement in environmental outcomes. So the more we know about this, the more we can have the right kind of sensors and the right kind of models that say, this is the level of fertilizer that I need in this area as opposed to this area over there. I'm going to deliver that fertilizer properly. I'm going to monitor it and see, did I in fact achieve the change in the chemical composition that I was looking for? Or do I have to adapt my internal model because for whatever reason, the ecosystem of the soil and the fertilizer and the water and the temperature and all of those other factors didn't respond the way I expected. I expected to achieve this outcome by this amount of fertilizer, and something else happened. Safety, repeatability, and reliability. So far, we haven't designed robots that will come in hungover, come in grumpy and distracted, and that's kind of what humans do. We're human, we're fallible. So even though we're introducing safety risks, we're also mitigating many of those safety risks because computers never ignore what's going on, almost never, since we said, of course, that things always go wrong. Access to expertise regardless of location. I was on a flight once that had to make an emergency landing in this tiny, tiny airport. It was the first airport that this jet could land in after having crossed the Atlantic. And they didn't have a mechanic there who could actually diagnose the problem my engine had. And so we had to wait for them to fly a mechanic from somewhere else. With the systems that we're talking about now, with some of these artificial reality, mixed reality applications, the mechanic that was there could have worked with the mechanic wherever he was to have fixed my engine, and I wouldn't have been nearly as late. So we can have access to expertise regardless of location. We are further breaking the tie to physical locations that things like cloud computing and cloud storage have already done in some ways. Protection from harsh and hostile environments. There are places that you would far rather send a robot than a human being. Increased capability. When you think about the work in certain jobs, and I'll pick on pathologists for a moment, if the vast majority of the slides that you look at are all normal, you're going to spend a lot of time saying normal, 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 normal. What if instead you automate away the low-hanging fruit? Even if the false positive rate is high, that just means a person is going to look at it. But everything that was taken away allows the human to spend more time looking at the things that actually require human intelligence. You can allow the human to focus their attention on the things that actually require attention. We talk about this in terms of intelligent empowerment. Rather than trying to automate away a task, automate away the low-hanging fruit of the task to free up the human to make more complex decisions, to deal with more complex situations. And improve situational awareness, because we have better and better models of what the real world is actually like, what is actually going on in a particular location. So, what would this world look like? What can we imagine? What are the things that we can enable in our country, in our society, with this new technology? I've talked a lot about things from the economic perspective, from manufacturing, but the societal implications of this as well are something. What can we imagine? How can we use this technology to improve the lot of humans on this planet? We're limited in many ways right now, far more by our imagination than by the technology that's available to us. But what are our responsibilities? We are getting to a stage where we as technologists do have to accept the responsibility that we are deploying technologies that even we don't understand. And if we don't understand them, The broader society clearly can't understand them. Our politicians cannot necessarily understand the impacts. So we have to think about what are our responsibilities as technologists to make decision makers aware of the risks that they are facing, to make our politicians aware of how they need to think about these problems. And we have to make sure that we're doing this in a way that allows us, hopefully, to keep a bit further ahead of the technology than what we've seen at the moment. There are systems being deployed in life-altering situations that we know are flawed. I read a very interesting case study about an application that was being trialed in a hospital to determine whether patients after a particular surgery should be sent into intensive care or not automatically. And they excluded from their training set a particular set of patients because they always put them into intensive care. And so that never got into the model. This was asthma patients were always put immediately into intensive care. And then they trained up the model and they started testing the model. And they trained up two models. One, using a technique that resulted effectively in a deep learning neural network that was very difficult to understand how it was actually making the decision. They used another learning technology where it was much easier to discern what was the decision-making process. And they realized when they actually looked at that other model that it was miscategorizing what to do with asthma patients. And if you would have just deployed that system and said, now, this system is what determines whether or not somebody goes automatically into intensive care, asthma patients would not have been put into intensive care, and people would have died. So the fact that they actually trained up two different models to try to understand on what basis it might learn was something that was noteworthy enough for this article to talk about it, because very often we're not doing that. In the United States, they are using trained models to determine the risk of somebody reoffending, to decide whether or not to offer them parole or to offer them probation or what their prison sentence should be. And there are some studies that show that those models are no better than random at predicting that probability. But these things are being used in the criminal courts in the United States. So we as technologists haven't yet gotten the right conversations going on, but we are expanding the footprint of where we are deploying these systems. It is our responsibility to make people aware of the risks that they're running, as well as the potential for good that comes from these systems. So those are our responsibilities, and it allows us then to go back to the previous question, which was, what can we imagine? How can we use this technology to create a world where we seamlessly move back and forth between the physical and the virtual world? What would that look like? Thank you very much. We should have time for a few more questions.
Thank you. That was a great, a little scary, but also positive at the end. I feel like with a bunch of the smart folks in this room, we can make some positive changes. Mm-hmm. But first question is, what's my name?
Adam.
See, she breaks the model already. I think you talked about this a little bit, but maybe the question that came in you could reemphasize is, why is it so important for us to really understand how AI works?
Because the way, at least the way we're training them at the moment, it's all based on what's happened in the past. And so it doesn't necessarily know, wait a minute, this is something completely different that I haven't seen before. So maybe I need to put my hand up and say, I don't know. Many of these systems don't know how to say, I don't know. They're just going to give you the best answer that they can. And in that situation, we can't really understand what risk we're running unless we know what are the characteristics of the training set that were used. How well does that training set model not just what has happened in the past, but how things might have changed in the future? If you think about how models might differ for some things, think about modeling of automobile crashes. In Germany, on the Autobahn, the model of what happens in a car crash is going to be very different than in a school zone that has much more controlled speed. Unless we know how those models were created, we can't know whether or not it actually applies in the situation we're trying to apply it.
Thanks for that clarification. So are you mostly scared or mostly optimistic?
I am, mostly is a strong word, but I'm leaning optimistic because I do think that we as a community of technologists have learned some of the lessons of history. We're a lot less, there are enough dystopians running around to tamp down the enthusiasm of the people. Well, we'll just deploy the technology and see what happens and hope for the best. But that had been somewhat the attitude in some places in the past. So I lean optimistic. I'm not sure I would say mostly optimistic, but I would say I lean optimistic.
I know, you're a mathematician.
I know,
so it's
I know, that precision thing. One of my graduate students sent me a picture, and it was an advertisement for Ben & Jerry's ice cream. And it said, some people's imprecision is other people's extra chocolate chips.
That's a positive outcome from that, right?
Yes, yes. That's good imprecision, as long as it's more chocolate chips and not less.
See, I don't like chocolate, so I prefer the less,
Ah.
but it's okay. Can we do one more round of applause for Rebecca?